And so we get 9 more neutrons, right? And those 9 neutrons can activate 9 U-235s, and in the process it's going to produce 27 neutrons, and those 27, and then we have this cascading effect. This cascading effect is called a chain reaction, right? In which things don't grow linearly, things grow exponentially. And so there's the risk of a nuclear explosion. You know, chemical explosion is pretty violent, but a nuclear explosion is going to be orders of magnitude worse. And so, you know, this chain reaction where what an explosion is too much energy is released in too short of a time period. And then we get an explosion. And if you have gases produced in the process, you know, you'll have like a detonation type where you get a pressure shock wave. Well, this is going to create quite an explosion. But you know, how can you prevent this from going out of control? Well, how you can prevent this from getting out of control is by using less than what is called a critical mass of the uranium. The critical mass of uranium is supposed to be like a grapefruit size quantity of uranium, and the grapefruit size quantity, you know, you'll have enough mass there that it can trigger this chain reaction, which can result in a nuclear detonation. But if you have a smaller quantity than that, then they say you shouldn't be able to. Although, you know, there are different levels because, you know, on some of the videos they show, you know, where the reaction doesn't quite result in an enormous nuclear explosion, but the reaction results in a violent detonation which destroys the building. And so, for example, I think in New Mexico they had one reaction that started to get a little violent. It was subcritical mass. They didn't have enough, and ended up blowing apart the test reactor there. There's a video on YouTube, I was looking for that, where, you know, some people are saying that is some sort of detonation, you know, nuclear detonation, although not at the level of a nuclear bomb. But if you keep subcritical mass, then in theory you aren't going to have an explosion. So that's what we have in nuclear reactors. We have less than a critical mass of uranium, so it can be controlled. Another way to control the reaction is because this electricity has to be produced on demand. Although, you know, the reason it has to be produced on demand is because of how do you store electricity? Batteries. The problem is are you going to build a huge warehouse full of batteries to store the electricity that's being produced? No, it's too costly that way. And so they just produce electricity on demand. So if there's high demand, they want to generate a lot of electricity. If there's low demand, then they want to slow it down. And so is there a way to speed up and slow down this reaction? Yes, there is. And one way of speeding up or slowing down this reaction is by using neutron absorbers. Neutron absorbers are called control rods. And something like boron nuclei are especially good at absorbing neutrons. And so if you place these control rods in the vicinity of the uranium, then it'll absorb the neutrons and slow down the reaction. And if you lift the control rods out of there, then it'll speed up the reaction, generate the heat. And so let's take a look at this. Here. And so you have control rods, and then you have fuel rods. And so the control rods go between the fuel rods. The fuel rods are just these tubes in which they have these pellets of uranium and some kind of ceramic oxide. In fact, I didn't really know what these. I'm going to go to. There's an interesting YouTube video here. Showing the nuclear fuel rods. Well, these are the nuclear fuel rods. here, an array of them. And so nuclear fuel rods, brittle. I forgot to look this up this morning. It's been a while since I showed this video. Okay. Well, let me continue what I was talking about, and then we'll come back to that. Well, anyway, where does all energy goes? All that energy goes into heating of water here, and so there's an internal, what we call, water circulation system here. This is completely sealed, and so just the heat goes straight to the water, and this whole thing sits in water. So I guess you call it water cooled. And then there's a heat exchanger here. The heat exchanger is on another system here, and so the heat's transferred to another water system in which, in this case, we boil. So this one's got to be under high pressure because this water shouldn't boil into steam. And as long as the pressure is high enough, the boiling point of water is going to be elevated, and so it shouldn't boil. But over here it's not. It's going to be probably under normal atmospheric pressure, and so this water is allowed to boil into steam, which drives a turbine and generates electricity, and then they can condense that water back down. They condense that water back down by having a cool source of water. So nuclear power plants have to be built next to the ocean or rivers, because then we have the cooling water come in here. Exhausted out here. And so this water here is in direct contact with the fuel, but this water here and this water here is not, as long as there's no leak.
How long can the water be with the core? Or do you have to keep changing it?
The water?
That's in touch with the rods?
Yeah. The water that's in touch with the rods, I think is just, I don't know if they ever exchange it. You know, I think it's just there. But, you know, what happens is corrosion. Too much stuff gets into the water, then you'll have corrosion of the pumps, and you'll have corrosion of the control rods and other structural features. I think that's what happened at San Onofre. Does somebody know San Onofre? Like something happened either with the fuel rods or something where they were getting accelerated corrosion. And so I'm not exactly sure. That's a good question. All right, so that's it for this, except the problem with this is what? Well, there are a lot of advantages. You know, the advantages of nuclear power is there's no CO2 emission. You aren't burning fossil fuels. Disadvantage of nuclear power is what? Yeah, the waste part. Also meltdown. Do you know what a meltdown is? Yeah, something like Chernobyl, although Chernobyl was a different style reactor than this, or Fukushima, you know, in which if you don't have water, let's say if the cooling system fails here, what happens is uranium's melt. And so as it gets hotter and hotter, eventually it's going to melt. It's just a heavy metal. And when it melts, then it could breach, the containment. And so that's what they think happened. Everything's contained in concrete here. So if this melts to the floor, starts eating through the floor, then it can breach. And they say eventually melt through, because it's going to be so hot it'll eventually, and it stays hot because, the nuclear reaction is ongoing. It stays hot, and eventually it's going to hit groundwater and cause some steam explosion, which is going to spread radioactive isotopes everywhere. All right, so that's that. Okay, what else do I need to talk about? Rates. What about the rates? I talked about, did I talk about the cyclotron? Okay. All right, let's talk about transuranium element. Here, we talked about linear accelerator, this one. The transuranium elements are all these man-made elements here on, and they're just made by accelerating two nuclids into each other. And they have different accelerators. Like this would be a cyclotron, where it just goes in circles here. Accelerate those. That's all I want to say about that. The rate of radioactive decay, all radioactive decay processes are first order. And these are characterized by their half-life, not the rate constant. Half-lives are a little easier to deal with. When we look at the first order kinetics, the equation looks pretty much the same, except this is a little different. Rather than ln of concentration at time t over concentration at time 0 is equal to minus kT, this is ln of activity or number of nuclids at time t versus number at time 0 equals minus lambda t. Lambda is the rate constant here. T1 half is the half-life here. And so the exact same equations. And so you could do calculations like in chapter 14. Let's take a look at some of the half-lives for some of these. Like tritium has a half-life of 12 years. Carbon-14, 5,730 years. Some of these are very short, though. Let's find some short ones. 10 to the minus 3 seconds. Some are very long. If you look at it, uranium-238 is 4.5 billion years. The 4.5 billion years, after 4.5 billion years, you should have half of your original. And then after another 4.5 billion years, you should have about 1/4 of your original. And so how long would it take typically to decay? And so a lot of people say, maybe 5 half-lives to get to about 90%. Some people say about 90% reaction should be pretty much over. But, or its activity should have gone down quite a lot. So let's take a look at half-life. So 1, 2, 3, 4 have 4 half-lives, about 5 half-lives. Pretty low activity. This is P32. P32 is used a lot by biochemists. This phosphorus occurs in a lot of metabolic pathways, so they can follow it, the radioactive P32, using a Geiger counter. Another application of some of these radioactive isotopes is radiocarbon or radioactive dating. It's not just radiocarbon. Carbon-14 is formed at a constant rate by the bombardment of nitrogen-14 with neutrons. Neutrons are produced by cosmic rays. We're continually bombarded by cosmic rays. So this is a natural process here that occurs. Carbon-14 disintegrates by beta emission. And so carbon-containing compounds in living organisms are in equilibrium with the carbon-14 in the atmosphere. That is, these organisms replace carbon-14 atoms that have undergone radioactive decay with fresh carbon-14 through the environment. But once the organism is dead, it's not going to be replacing that carbon-14. And so then it's going to naturally decay. That's great. And so here's an example of carbon-14 dating. You have other isotopes you can use for dating, lots of them. Because carbon-14 is only good for a certain number of years, let's say thousands of years, but if you want to go back more than that, then you can look at some of these isotopes here, and usually you get, ratios. Like this is called, like, lead would be the daughter product of U-238 decay. The uranium would be its parent, so it's parent-daughter ratio to look at, or daughter-parent ratio. And so here's more dating. We don't have to worry about this too much, but okay, energetics. And I needed to see one other thing here. So we talked about the energetics. We talked about the mass defect. Talked about the effect of radiation on matter. A Geiger counter. Geiger counters like this, they have like mica, which is a mineral, a mica window, which allows the ionizing radiation to get in here. And normally gas atoms are neutral, but if you have ionizing radiation, it creates ions. Ions conduct electricity, so if you put the anode here, some high voltage source, and cathode here, then as you create ions, it's going to close this circuit, cause a signal. You can count it. So that's a Geiger counter. Geiger counters, though, what about alpha particles? If you have alpha particles, can an alpha particle make it through this mica window? And it turns out no. Geiger counters, this is going to detect gamma, radiation, X-rays, and beta, because those can penetrate this. But for alpha, you have to use a different type of counter. And so there are counters that you have to look, but there are counters that you can purchase that will measure both alpha and the other particles for electromagnetic radiation. Radiation dosage, a radon. Okay, so let's look at applications. So cancer therapy, you could use gamma rays to kill cancerous cells. The problem with gamma rays is they also kill healthy cells. So what they're trying to do is focus the gamma rays just on the cancerous cells, kill them. They're used as radioactive tracers. My friend got a job at the oil refinery, and he'd just walk around with a Geiger counter around the pipes to detect any leakages. What they did is they injected tritium, I think, into the, was it the Geiger? It was some radiation detector, because tritium's an alpha emitter, as I recall. No, tritium's not an alpha emitter. But anyway, he'd walk around after they injected the tritium and just look for leaks, wherever he measured radioactivity. There were leaks there. It's used as a tracer. The tracer in biochemistry is the P32. P32, they dope certain things in and see where the phosphorus ends up. It's used as tracers for chemical mechanisms. If you want to figure out what the mechanism is, what you'll do is you'll incorporate some of the radioactive isotope into some species, and then just follow that species through a mechanism. And so here, this proves that iodate is produced by reduction of per-iodate and none by the oxidation of iodide. And so this just shows how the things are reacting at the atomic level. Neutron activation in analytical chemistry, analytical analysis, they're trying to figure out what elements. Neutron activation was used to establish that this painting was not painted by Rembrandt, based on. radiation processing. For example, here, irradiation. Like these strawberries have been irradiated, these have not been irradiated. There's a lot of misconception here. You know, just because the strawberries have been irradiated, does that mean these strawberries are necessarily radioactive? Are they radioactive if they've been radiated? No. This is to kill off fungus and whatever else.
What is irradiation?
Irradiation is like using X-rays or gamma rays or whatever, ionizing radiation to kill the living organisms on there. So irradiated food. Well, that's close to about it. There's only one more thing I need to show, and that's a radioactive decay series. Just skip earlier. Here it is. This is a radioactive decay series. Yeah. This is starting from U-238. And so you can see this would be like an alpha emission here, alpha emission, actually alpha, beta, beta, alpha, 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 alpha. Over here it could go beta or alpha, a branch here, alpha, beta or alpha. Eventually, we end up at lead. Lead-82 is not radioactive, so it doesn't undergo further decay. So this is stable. And so this process, has a half-life of 4.5 billion years. That's a long time. Along the way, it produces lots of different radioactive isotopes. Here. And so they have these decay series for a lot of radionuclides. Here is a different representation of the exact same thing. This is more compact, a lot easier to see, but we both end up with lead. All right, so work through these homework problems here. If you have any questions on these, we can answer them tomorrow. All right, so what do you guys have questions for the final exam? You can do some review right now.
Are the questions going to be, because I know like for 1A, you said that there was only going to be one answer, so is that the same for 1B?
Yes. There's, on multiple choice, there's only going to be one answer. Make things simple. Just pick the best answer. None of the questions are going to have multiple answers. All of them will have just one single. Roughly 60.
Is there any
About 3.
Is there any fear response?
Yeah, maybe less. I try to keep it down because 3 points is kind of a hit. Yeah.
Is there any fear response?
If I do give you a longer calculation in multiple choice, then I have to compensate for it. It's not to say you won't have like a multi-step maybe calculation. You could. It's just you aren't going to have very many of them because they take too much time. And so maybe you might have one, you have to do, but most of the calculations are going to be like single step more or simpler calculations, right? Otherwise it would take too much time. Free response, there's not going to be any other than only the reactions, right? You're going to have a minimum of 3, 4 maybe, minimum of 4. I haven't decided yet. Yes. Yeah, I think you can guess why I said they're going to be 4. Can somebody just explain it to me? Hmm?
Redox.
Yeah, I'm gonna have at least one metathesis. You know, I say this all the time, but it's funny because some people will do try to do everything metathesis or everything redox. Don't. You can kind of get a clue. I mean, if it what kind of reaction it should be, because you're going to have one metathesis at least, one redox, one acid base, maybe 5. One acid base Bronsted, one acid base Lewis. Maybe Lewis, no Lewis. All right, maybe one acid base Bronsted and one skeleton redox. Although skeleton redox is Chem 1A, maybe I'll throw that. Skeleton redox? Well, since I had 5 of them on the homework assignment, I better put at least one on there.
So I would make an acid 6, redox, acid base.
Yeah, you know, just do that homework assignment, the 20 questions there, and I think you'll be very well prepared for the final exam. No, 60, just 60 multiple choice. Or maybe more.
It's going to be around like 200 points.
Yeah, it's still going to be around 200 points. I believe I can't remember.
It's just going to be around 20%.
No, it is. Yeah, it's going to be around 20% of your total grade. We're going to have less than 1,000 points, so it's going to be 20% of that. So I'm just going to adjust the points to make it 20%. I don't want to make the final work too much because. Yeah. Study your old multiple choice questions. Those are good.
So is it more going to be like straightforward, conceptual questions, or more like?
I think so, but you know, if I say so, I think the problem with the last time I gave this final was I said, oh, okay, just make sure you know the basics of each chapter, and I think that gave people a false sense of security because I don't think it was one of the worst performing semesters I had on the final exam. I've had way better. And so I don't want to give people a misconception that all the questions are going to be easy and basic. You know, it is. If you think about picking 4 or 5 questions per chapter, then you want the most basic concepts and the most basic calculations. You know, to make sure that at least you've gotten the basics down. You know, the final exam is not the test. You know, if you could do the advanced, the advanced problems, it's just to see, you know, did you get the basics down? But what I consider the basics might, I don't know, you know, for example, I would consider it basic to know, you know, what types of methods do you use to solve equilibria? I would think that's basic, you know, what are the methods that you use to solve equilibrium problems? Stepwise, simultaneous, etc. And so, I gave a question like that, related to that, and I was surprised how many people got it wrong. And I was thinking, that is basic, you know? And so this was the last time I gave the test. So something so basic that, and I thought it was an easy question that too many people got wrong. So I don't want to say it's easy, you know, because nothing is really ever easy. And if it turns out to be easy, then great, you know. But you should prepare. And I think a lot of people also, they thought, well, you know, my grade is okay, you know, going into the final. You know, they thought, okay, if I just do the same, but the same is, you know, on the final, we're going to have 2 homework assignments in addition. One is worth 10 points, the other is worth the other half of chapter 24. Actually, and the reactions homework is worth 10 points, so that'll help, you know, make it. Plus, I had the 10% bonus on the final, you know, and so if the final, let's say the final were 200 points, the total possible points would be 220 points. And so I thought, you know, you know, people who are doing like B work throughout, and then on the final, let's say, even with that 10% bonus boost, you know, ended up dropping their grade, you know, to a C, and they're shocked. A lot of people were shocked that the grade got dropped. And so,
What is the reaction score?
It's on Piazza.
on Piazza, right?
Do you want the like non-ionic and ionic equations?
But yeah, then again, I don't want to scare you too much. You know, so this is what I do. What I say is to everybody who studies for the final, you know, just try your hardest. You know, if there are other classes that you really need to focus on, and less on chemistry, you know, you just gotta, what you gotta do is you just gotta see how much time you have, and then just divide it amongst your classes, and that's all you can do, you know. But the thing is, you know, some people will say, I want to see what my grade, because then I know if I can relax on the final. I would never relax on a final, never, because a final is so unpredictable, you know. A final, I don't know, unless you could totally blow the final and still do okay, you know, then maybe it's okay, but, you know, I still take it very seriously. Because it is 20% of your grade, which is kind of a big chunk of your grade. But again, it's just, you know, my main thing with the final is to see, you know, did you get the basic? Can you do the basic calculations? Basic calculations have changed. You know, when we're doing in chapter 15 a basic calculation, okay, then it's pretty simple, you know, just a simple ICE table. But by the time we hit chapter 18, then what I consider a basic calculation is all of a sudden a lot, you know, would have been a difficult, you know, problem earlier. You know, what types of techniques do you use to solve, you know, or simplify ICE calculation? Simplifying assumption. I consider that basic by this time. You know, some people will think, oh, simplifying assumption, maybe that's more advanced, but to me that's totally basic. Should be basic by now. What else? Reset. Now, by the end of the semester, I consider reset. If you can't do a reset, then I don't think you have basic skills, you know, if you can't do a reset. And so I consider that basic. Yeah. What else? Successive approximations. Yes, I consider that basic, but you know what? I'm not going to give you a successive approximations problem because that takes too much time. So you can just forget about that one. Right.
Do you have to memorize all the different equations?
You do not have to memorize all the different equations. No. Yeah, I'm going to provide those. Right.
What kind of table do you given? Are any charts at all?
You're going to be given all the charts. You know, the way I've normally done the exam in the past is I've given 2 parts. This is like Chem 1A. Do you guys remember, for you, those of you who had me in Chem 1A, in Chem 1A I gave like a 2-part exam where I give the reactions separately from the other. And so Am I going to do it this time? Probably. As long as everybody doesn't have a programmable calculator, I'll probably not do it. I'll give it all at once. You know. You have just a basic calculator. That's it. The reason I started doing that is because, you know, one semester I had a student scrolling through their calculator when I'm giving a chemical reactions quiz. There were no calculations. They're scrolling through their calculator. I'm sure you guys are, well, I'm not saying you guys, I'm sure the students are much more sophisticated now in ways to do it. What's that?
Well, I guess you needed to balance those equations.
Yeah, that's true. Balancing. I wonder. I haven't watched the last video he has. This guy's an interesting guy. He's a former. He has a master's in nuclear engineering, and he was a former, I think, executive or vice president at 3 Mile Island and other places. But he got his hands on some of the fuel rod holders, and then subjected it to some heat treatment. So it was pretty interesting. He has some other interesting demos that he does. So let's see if I can show this. Okay. Well, looks like audio's not working here. I'll show this tomorrow in lab, but that's a fuel rod there. And no, it's a very tough material until they get the torch out. And this is mild heat treatment here.
Is that how small they are?
Yeah, that's an actual fuel rod. There's no fuel. The fuel is in these little pellets. He shows it in his hand here. That's what the fuel looks like there. It's not actual fuel, but they make it in pellets like that, and then fill the rods up with those pellets. But he's talking about Fukushima, how the nuclear fuel got scattered everywhere. What happens to these rods? But I'll probably show this tomorrow since there's no audio in here. There's another interesting one with the hydrogen, so we'll talk about that. All right, so let's just continue with the review then. Here. So you should be able to do those, you know, things like simplifying assumption, right? Things like resetting, because, you know, in the past, some of the problems have not been easy to solve without resorting to that. And so we spent, a lot of people think Chem 1B is easier because there are fewer topics than Chem 1A, and some people think it's more difficult because the calculations are more difficult, that type of stuff. But if you go back to chapter, let's say we started off with chapter 15, right? Well, 24. So a few questions from chapter 24, what would you guess? Maybe one nomenclature question, one chemical formula question, right? Some question about ligand, yeah, acid base, ligand, central metal. Uh-huh.
How many questions will be from chapters 24 and 25?
Okay, chapter 24, we're going to have extra questions in there, you know, because like a few extra questions. And so chapter 24, let's continue with it since we'll just cover it all at once. You're going to have questions about isomers, you know, maybe 1 or 2 questions about isomers, you know. An example, what would you think an example would be? You know, which of these compounds shows cis, trans isomerism or mer face isomerism? So you have to draw them up, look them up. Maybe another multiple choice question might be, which of these compounds is? Well, the 2 major types of isomers we talked about, the geometric and the optical. So which of these compounds is optically active? You know, the geometric is cis, trans, mer face. You know, optically would be the, what was the optical? What was the definition of optical? It rotates light, but how can you tell if it's optically active? It's because it's an isomer that is the mirror image and not superimposable. So it's a non-superimposable mirror image. That's what an optically active isomer is, an enantiomer. And so that might involve some drawing, maybe. You know. What else would I ask, do you think? Well, now we're up to how many questions? Maybe 4 or 5 questions already. I can't push it too much farther, right? Otherwise I have too many questions from one chapter. Well, what else do you think is important from that chapter? Yeah, crystal field theory, right? Crystal field. What types of fields do you have? Octahedral, tetrahedral, and square planar. And so you might get a question about which of these, you know, is paramagnetic or something like that. You know. There you have to know about strong field and weak field, and you'd have to know what splitting pattern it is, you know. And so that's what, how many questions are we up to now? 8, 7? You know, somewhere around there. You know, I can't ask too many more, otherwise the test is going to be all 24. I don't want that because I want everything. But I'd probably ask you about, you know, things like not only magnetic, what other properties? The color. So I might ask you something, because remember that we were talking about crystal field theory describing the magnetic and optical being color of these complexes, and that's pretty much maxed out right there, otherwise it's too much. And so in this sense it's kind of good for, you know, if you think 3 points per question is a lot, if you have, like, say 4 questions on the final and each one's worth 25 points, you know, there's a lot more risk there. And so this is still spreading it out, but I know it's a kind of a big chunk. That's why there's, on multiple choice is one of those harsh things where it's either all right or all wrong, because like I said, I'm not really going to give much partial, but this is why you have an extra 10%. That is, you're going to have a whole bunch of extra multiple choice, so you don't have to feel too much pressure about getting one wrong. You know, I was looking at a test, somebody else's test, and if they missed one multiple choice question, they were down to a B. You know, that was pretty harsh, I thought. It's in a math class. Most multiple choice, they have a lot, you know. I'd like to put a lot more on there, but it's too much time. You know, you got to think, you can't spend more than 2 minutes per question, roughly. Some of the questions are going to be quick, easy. So that's chapter 24. Chapter 25, what am I going to ask you from chapter 25? Well, let's say, I can ask you anywhere from, let's say, 5 to 10 questions from chapter 25. What do you think I'm going to ask you? Yeah, maybe types of radioactive particles. Maybe, you know, do you know what an alpha particle is? He24.
That's probably, what do you think the most important particle? If you're going to learn one particle, which one do you think is the most important? Probably. That you see a lot of. Like, no, you know, in that decay series, what was it? Alpha, 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 alpha. You know, and some betas thrown in there. So when you study, you got to think, you know, in terms. Obviously, I can say, okay, that's easy. I want the more obscure stuff. You know, the more obscure stuff, but that's not the purpose of the final. The purpose of the final is, you know, I want to just make sure. The purpose of the final is, okay, maybe you blew an earlier test, right? But did you at least get the basics from the chapter down? That kind of thing. And so alpha, beta, then these nuclear reactions, you know, I might give you something like this. This is a multiple choice, you know, what is this, you know, question mark, whatever. Or what is this, you know, A, B, C, D. Kind of thing. All right, what else would I ask you? Half-life, I could ask you that, but what was more important than that? Have you gone back to your notes at all from? Well, what is it? Why is it radioactive? Well, we talked about
Stable.
nuclear stability, right?
For nuclear stability, is an even neutron, even proton, like relationship more important than the 1-to-1 ratio?
Okay, that is no, because if it's even and even, and it's not for heavier elements. It's not. Well, it depends, because you could have, let's say, 20 protons and 22 neutrons, and then it's okay. But if you have the same number, like 20 should be exceptionally stable, right? But as you get higher and higher, then you need more neutrons to make the most stable.
The homework problem that brought it up, it compares lithium-7 to lithium-6. And so it says that lithium-7 would be more stable in that case.
Yes. Lithium-7 would be more stable because that has an even number of neutrons, right? Or let's see, lithium is 3. And so lithium-7 would have 4 neutrons. Lithium-6 would have 3 neutrons. And so that would be a case of odd, even versus odd, odd. And so odd, even is better. And so you wouldn't have to know some of the basic trends in nuclear stability, and that is although I'm not going to give you too many questions from chapter 25, because chapter 25 was quick, right? And so
I have 5 to 10 questions.
I don't know. Yeah. Let's see, what else could I ask you?
Any calculations?
Maybe a calculation.
But we didn't go.
What's that?
We do calculations.
Did we do calculation? Did I do a calculation?
Delta V.
Yeah. Yeah. The other thing is, you know, there's certain things too that you can, maybe there's going to be calculation. I got to write in all those. You know, when you're pressed for time, let's say you don't have enough time because you got too many things to study for, then you want to study for the higher probability questions. And if I put that one question in there, how much room does that take? You know, have you noticed something? I don't like to waste a lot of paper. And so that question is going to take up a lot of space unless I write the data on the board, which I could, you know. But the calculation should be easy. Didn't we do a calculation? Didn't we do the tritium calculation? Tritium and deuterium? Easy calculation. You know, if I was studying, I'd be really thankful if a calculation like that came myself, you know, because I would think that would be easy points. But, you know, maybe not, because it's multi-step, because not only do you have to calculate delta M, and then you have to figure out, yeah, you have to convert U to kilograms, and then, you know, C, square that. So, when we look at it, you want to also look at the homework that we did. Homework, we're pretty much curious, you know, when is 99% of, okay, which one loses more than 99% of their radioactivity in 1 month, you know? And so this is just some basic kinetics, you know, if you have 90% reaction or 99% reaction, you know, how long does it take? Here, you know, on some of these, since they're multiple choice, you don't necessarily have to do calculations for all of these. You know, some of these you can figure out without doing any calculations. Is it possible? Yeah, so yeah, it's possible. You can kind of ballpark the answer and then narrow it down to 1 or 2. I guess. You know, so when we're looking at it, after 1 half-life, 50% remains. After 2 half-lives, 25% remains. After 3 half-lives, 12.5% remains. After 4 half-lives, 6.25% remains. That means more than 90% has reacted by 4. After 5 half-lives, you know, you can kind of figure it out without doing calculations sometimes. You know, because a lot of people are curious, you know, how long will it take for this to decay? Oh, very long time, not just 1 half-life. You know. P32, let's look at P32. They're using this in biochemistry a lot. You know, after it's almost 7 years, 4 half-lives, long time. Stuff is going to be around for a while. Iodine, you know, the iodine, like in nuclear power plants, that has a half-life of 8 days. And so on the news, especially around Fukushima, they're doing the iodine measurements and saying, you know, if it has a half-life of 8 days, you know, when does its activity decrease to a level where it's pretty much considered safe? Is it after 1 half-life or after how many half-lives? So you would go on, you would go through this and then see, but I don't know how many questions I'd ask from this chapter. Probably ask something about, you know, effect of radiation on matter. Like if you wanted to know your radiation dosage, which one would you rather have it in? Rad? Curies? REMS? Siemens? Yeah, REMS. Fission, fusion,
You know, this is just stable. Small nuclei would like to fuse, right? Large nuclei like to fizz. Yeah. So just some basic questions here. Nothing too terribly in depth. And so that's what you should do when you're going back through this stuff. You know, just think. You know, you might think that's a lot of questions, 5 questions to, let's say 5 to 8 questions per chapter. It's not. You know, if you were to go back through each chapter and think, what if I were going to ask you 8 questions, what would they be? You know, could you think of the 8 most important things you would think, in your opinion, that I would ask? All right, that's it. Is that it? Oh, how late do we go till? 55. Oh, 55. Wow, I finished really early. Chapter 25. I was thinking I could talk more about nuclear chem, but yeah. All right, let's talk more about what do you guys want to review?
How about the chapters 17 and 18? What kind of question would you get the most attempt?
All right. Chapter 17. You know, chapter 17 is tough because the calculations were more involved, right? When you're doing chapter 17, you had step I. Remember step I? Step 1, step 2, step 3. You know, and so you got to think. If I ask you one of these 4-step reactions, then that's going to be more time-consuming, and then I have to. And so I'm not going to ask too many of those, would I? Maybe if I were asking something like a diprotic acid and you're in the excess base region, you know, it's involved, right? It's still, you should know that because it's a basic calculation. No, well, I can't ask you too many calculations. I might do simple, like a monoprotic, or I might do a diprotic, make it longer. But you're going to have a calculation, for sure you're going to have a calculation where you have to do the basics. The basics would be step I and then step 1 and step 2. You know, you guys remember that? If not, you know, it's a good time to review. What other types of calculations? You know, buffer calculation, Henderson-Hasselbalch, for sure. You know, you're going to get a buffer. What else, as far as calculations go? Maybe like a KB, although KB was chapter 16, probably. And so you go through and you think about maybe one indicator problem. Although I didn't really talk much about indicators today. But you should know, you know. Well, I mean, what? The first thing you should have been reviewing are your old multiple choice questions. Have you been even reviewing those? Have you? Good, good. If you've been reviewing those, this should not be a surprise. What? You know, I gave you an indicator question on an earlier test, right? I thought it was important enough to include it there. It was a very simple one, I thought. You know, you could see something comparable. But, you know, the calculations, here's the difference. If you go back on the old test, the chapter 17 test, I put the calculation in the free response. And I didn't put these lengthy calculations in the multiple choice. On this test, I have to do it a little differently, you know, so I have to think of an appropriate calculation to put into the multiple choice. You know? But I don't want, you know, I don't want an advanced level problem there. I didn't really put an advanced level problem on your 17. All right, so buffers and titrations and anything else?
The matter we're not gonna draw the batteries again, right?
No.
What do you think? No. No. Maybe some people would like to draw it again. So you go through here and you look. And then you think about conceptual questions, buffer capacity. Ideal pH. We also had certain things. Do you guys remember this equation here?
Spider?
That's
I like the name.
That's the one that
or like
Amphoteric.
Yeah.
Amphoteric.
What was this spider?
Is that enough for 17? Chapter 18, you're going to have a KSP calculation, obviously. Solubility, right? You're going to have a common ion problem. Common ion. What else? Solubility in pH. Remember that? You're going to have a KSPA, maybe, and a KSPF. Maybe some conceptual problems. This is helpful. You know, if you want help with your visual MinTech, look at page 792. You know, this is what I was asking for was just some comments about Visual MinTech, you know, versus our calculation. Here it is. Our calculation is in black. Visual MinTech is all of this, blue and black. Now, this is very simple. That's the kind of thing I want. But I wanted to know, you know, and let me just spell it out for you. Basically, I just wanted to know, is it okay to ignore all this, or not okay to ignore all this? You know, the same thing goes for your crystal violet. You know, when I asked for some kind of comment on your rate law, does the rate law look normal to you or abnormal? You know, what orders did you get? Tell me the order you got in crystal violet. First order. What did you get in hydroxide? You got some weird order in hydroxide, maybe? You got first order in hydroxide? I want some kind of comment about that. It doesn't have to be long, it could just be a sentence. Maybe you got lucky, everything worked out perfectly. But the problem is, you know, do these numbers make sense to you? Well, the problem is that people do the calculation and just leave the number as is, and they don't think about the numbers at all. The numbers imply or what they might mean. You might not know. I mean, it could be hard. You know, you get some weird thing and you have no idea. Is that experimental error, or is that real? You know, there's an example of this. What would you do if you're doing an empirical formula and you always got this? You always got MnO 1.98. And then you think, oh, that's just experimental error. 1.98 is rounded out to 2, MnO2, right? But if it were experimental error, then sometimes you should get 198, and sometimes you should get maybe a little higher, and then they should average out, right? But this is very weird because lots of people repeated this, lots of different labs repeated this, and every single lab got 1.98. A lot of people say, let's just round that to 2. But if everybody's getting 1.98, maybe it's real. And you know what it was? It's real. It is really, this is what we call a non-stoichiometric compound. A non-stoichiometric, how do you get a non-stoichiometric compound? Because we're supposed to have 2, right? This is manganese 4. We're supposed to have 2. The way we get a non-stoichiometric compound, this is what they figured out by doing structure of this, is that there are a whole bunch of defects in the structure, and these defects cause the oxygen ratio to be 198. That 198 is very important because this gives this compound very interesting electrical properties based on having these defects in here. And if those defects weren't present, then it wouldn't display the electrical properties that it actually has. And so this is a story. And so a lot of people will get, oh, you know, I got an order for my hydroxide, and I already talked about this, I think, 1.48. I'm just going to round that. I'm going to round that to first order hydroxide. Is that okay? And so I just want some kind of comment. You know, I don't expect you necessarily to have everything figured out, but, you know, something should say that further, or maybe, I don't know, maybe fractional's okay, is it? I asked some people, they already figured it out. But anyway, just some kind of comment about numbers, you know. And so this is quite good for your visual MinTech, because this one figure here pretty much sums up the visual MinTech for me. And this is what I was looking for in your short report. It's a very short report, which is going to be nothing formal, right? But I just don't want somebody just to turn in the numbers. This is my visual MinTech, this is my homework, there you go. You know, without any kind of comparison. Does that make sense for what I want from? But maybe say, you know, oh, this is 10 to the minus 6 molar. 10 to the minus 6 molar, is that big? Is that small? What is that? Actually, visual MinTech would be mole out. This is 10 to the minus 6 mole out. This is 0.1 mole out. Well, what do you think? 10 to the minus 6 versus 0.1. Huge difference, right? Or maybe this is 0.1 and this is 0.1, and then, you know, you want to see, because what you're going to find out is that, you know, this is why, I'll tell you, this is one of the reasons why getting that PhD might take 10 years. Is you get these weird numbers and you have no clue what to do with, you know, to make any sense of them. I'll tell you though, you should have some clue what to do with these numbers, you know. But sometimes you get some weird numbers. You just don't work out, and you're thinking, oh my God, how am I going to figure this out and get out of here before retirement age sets in, you know? But this happens a lot. I'll tell you, the funny thing was, I was looking at some testing done by a nationally recognized testing laboratory, right? And they got, okay, mass of the crucible with the sample. The mass of the crucible was greater than the mass of the crucible with the sample, and so they got a negative mass for the sample. And they still, what did they do? They used that number. They used that number. I'm thinking, you know, what's the justification for using that negative mass? I mean, but they use that number, and then they're saying, oh, you exceeded the percentage of this. How can they say I exceeded the percentage when the error in this is that huge? You know, this is for testing for a standard, you know. And so I was thinking, yeah, these guys, I understand why they did it, because what else can you do? But you know, to base something on rejection or acceptance based on that, you know, I think a little more thought has to go into it. And so the whole thing was rejected because of the thing went over a certain percentage. It was surprising. All right, I'm going to stop here and then